All right, so this is the other method for doing a problem like number 13 or 14 when you are given a complex zero and you really just want to cry, but you actually have to do the problem. Keeping in mind that factors and zeros are directly related to each other. This one is going to have 3 zeros. It's going to have 3 factors. So I already know 2 of the zeros, which means I can noodle my way through 2 of the factors. They technically only gave me 1 zero, but I am a big brain and I know that the conjugate would also be a 0. So this is going to be 2 of my 3 zeros. So like with 12, let's say that you knew 12 was broken into 3 factors and you knew that 2 of them were 2s. You would have to ponder your way back and get to that third one basically by dividing out the 2 that you knew. So that's what we're going to do here is you would multiply these together and you would say, okay, that is what I now need to, so we'll call this x because we like to call things we don't know x. Now I know the product of these 2 is 4, so to find my last possible piece, I'm just going to divide by that 4 to find my last factor. So it's that concept just in big brain world. So we have to think about what factors come from these zeros. And I keep saying you're going to take x minus the entire factor value. And the reason the parentheses matter here is you're going to have to do some distributing. So we're going to do what we did up in that little 12 equals 2 times 2 times x. We need to multiply those 2 together and then divide our original polynomial by what we get to figure out this last one. So let's start by distributing this negative here. So I'm going to have x minus 1, and then that's going to change to plus root 3i. And then in the second factor here, this is going to distribute, and I'm going to have, sorry, that should have been an x. That's going to be x minus 1, and then minus root 3i. So back to my little 12 equals 2 times what example, I now need to multiply those together just like I did the 2's to find out what what's missing. So I'm going to take my time and distribute, and so I'm going to distribute the x to everything in the second factor, so I'll have an x squared, x times negative 1, and then x times the square root of 3i. Then I'm going to go ahead and distribute the negative 1 to everything in the second factor. So negative 1x, the negative 1 times negative 1 cancels into positive, and then negative 1 times this cancels into positive as well and stays root 3i. Now I'm going to go through and distribute the root 3i. So here I'm going to have an x root 3i, and then a minus root 3i. And then here I'm going to get a negative. Root 3 times root 3 is going to be a 3. I times I is going to be I squared. So this will end up having a value of plus 3. So at this point, the imaginary parts should cancel. So let me go through and see. I have a negative root 3i, a positive root 3i. I have an x root 3i, but a negative x root 3i. So when you multiply 2 factors involving imaginary numbers together, it needs to clear out, and it needs to produce something without any imaginary numbers. So I'm getting an x squared from this. I have a minus x minus another x, so I'm going to have x squared minus 2x. And then I have this 1 and this 3, so I have plus 4. So what that is doing is that's like the equivalent of the 4 in this example. It's telling me that the 2 zeros I know and the 2 factors that they are associated with have a product of x squared minus 2x plus 4, and that will go in evenly into my original polynomial, just like the 4 up here had to go in evenly to the 12 for me to find that last zero or factor. So now I get the pleasure of doing long division. And actually, The long division part of these is easier, I would argue. My concern right now is whether I have room in this spot, but I'm going to give it a go. I'm going to erase this and the end of this and see how we do. So I need to take that x squared minus 2x, whoa, I should write it in a straight line. X squared minus 2x plus 4, and I'm going to divide that into the original polynomial, which was 3x cubed minus 4x squared plus 8x plus 8. I do not need any zeros for space savers. So what do I have to do to an x squared to turn it into a 3x cubed? I need to multiply it by a 3x. So I go over here, put it above the other x, plain x, the linear ones, and now I'm going to multiply this 3x by everything over here. So 3x times x squared, 3x times minus 2x, and 3x times 4. So that's going to give me a 12x. So now I'm going to do that second row, and I'm going to go ahead and do subtraction. Sorry. So that is going to be minus plus minus. So that's gone. Here I get a 2x squared. Here I get a negative 4x, and I bring down my plus 8. Then I ask myself, what do I have to do to my x squared to turn it into 2x squared? And the answer is to multiply it by 2. So multiplying 2 by everything over there, I get 2x squared minus 4x plus 8. And when I go through to subtract, everything cancels, which I expected because I knew that was supposed to go in evenly. But what that just did is it found me my last remaining factor, which allows me to find my last remaining zero. So the answers are the same, whether I use this long division method or I use a synthetic division using the complex zeros. So you have to kind of try each way or pick a way right from the get-go and just practice that. And then you can utilize that same process each time that you're given a complex zero. You certainly don't have to demonstrate both methods. You can just pick one that you like best and go with it. Hope that helps. Bye.